Welcome back. And so this is COL 774 machine learning, and today is April 15th, 2020. Okay, so last class, right, we were looking at clustering, and specifically we looked at the k-means algorithm, right? And just to remind you again, right, this was sort of our uh, example diagram, and we were given a set of points I equal to 1 to m, and we wanted to estimate a ci for every I which belongs to the set 1 to k, which essentially denotes the cluster membership. And in the process we also computed this mu1 up to mu k, right, which represent the cluster means or cluster reps, right? And each mu L belong to Rn, right? So for example, in this case, this could be your mu1, and this is your cluster 1, and this could be your mu2, and this is your cluster 2. And to obtain this, right, we had a two-step process, right? In step A, we said estimate C's given mu's, right? And in the B step, we said estimate mu's given C's, right? And we essentially ran it until convergence, right? And this was guaranteed, or at least we sort of stated that this converges to the local optima of J mu C, right? So if you wanted to minimize this function, right, then above algorithm converges to the local optima of this JC mu, right? So this was our idea, right? The local optima of this function, right? And let me sort of draw a line here. Okay, so let's move forward. There are two remarks that I want to make before we proceed further on to the next algorithm. And the first one is the time complexity of k-means algorithm, right? And recall that J mu C was xi minus mu ci where I equal to 1 to m, right? So this is the objective function for k-means. And then we want to compute the time complexity in terms of the following quantities: m number of examples, n number of features in each example, and k the number of clusters. And what we will do is we will compute the time complexity in terms of these variables for each iteration, and then simply multiply by the number of iterations. Okay, so step A, right, which is also referred to as E step, which is estimating the C's given the mu's. What is the time complexity of this? Right, so let us look at this J mu C equation. So this will be order, right? So how do we compute C's? So for every point, we need to compute to what cluster it belongs to, and that's simply a computation of comparing or computing that point's distance from every cluster. Computing of distance of a point from a given cluster centroid takes order n time, right? Because there are n number of dimensions. Just write it properly, n, okay? And because we want to do it for k clusters, right? So there is k, and then finally we want to do it for every point, right? Because we want to compute this membership for every point. So this is n. So this a step complexity is order mn a, right? So once again, for every point, which is essentially m, a factor of m, we take this point to every cluster centroid, computes its distance, right? Computing the distance takes order n time because there are sort of n features, and you have to compute this norm for by summing up the square distance in every dimension takes order n time, and then you have to do it for every each of these k clusters, so order mnk. Okay, good. Now let us look at the m step complexity, which is the b step, which is we want to compute the mu's given the c's, and this takes order, let's say, so now we want to compute the centroids for each of the clusters. So let us focus on the computation of one centroid, and then we'll sum up over all the clusters, right? So for a particular cluster, right, to compute the centroid, we take all the points in that cluster. So let's say ml denotes the number of points in cluster L, number of points or number of examples in cluster with index L, right? And then we want to average over those points, and again averaging over n sized um, examples takes order n time. In some sense, right, we are averaging ml points, and each point has l features, right? So we have to average over each of these features, right? So it takes ml into n amount of time, and this is for one cluster, and we sum over l equal to 1 to k, right? Which is sort of equivalent to order, right? N comes out of this sum because it does not depend on L, and sum over all L's. ML is simply total number of examples, so this becomes order ML, right? Therefore, total time complexity of single iteration of k means is simply order, right? Just summing of time complexity from step 1 or step A and step B, which is order m n k, right? So if t is number of iterations, then the time complexity is simply given by order m n k. Okay, it's repeating that expression from the previous slide. The time complexity of k-means algorithm is order m n k t, where m and kt are as defined earlier, right? In particular, note that this is linear in m n k and also t, right? So right, which is not bad, right? So k-means algorithm runs in linear time complexity, both right, in terms of the number of examples, number of features, number of clusters, and I guess of course in number of iterations, because you have to do this computation for same for each iteration. Okay, so this is fine. The next thing that I want to do is failure cases of k-means, right? And this is important because this will essentially motivate us to go to the next set of algorithms, which is Gaussian mixture models, and also talk about EM, which is expectation maximization. So the first failure case that I want to demonstrate for k-means is as follows, right? So this is, let's say you have one set of points and another set of points here, right? And clearly there are two clusters that you want to be able to discover. In this, there is a smaller cluster here of points, and there is sort of a larger cluster of points here, right? And your mu1 and mu2 might be sitting somewhere here, right? But it is not very difficult to show that if you run k-means on this, even with the the correct mu1 and mu2, right? So even if you started with the actual mu1 and mu2, the kind of clustering that you will get will be something like this, right? And on the left side, this will be cluster 1, and on the right side will be cluster 2, right? And think about this, why this will be the case, right? In fact, in this case, you can even prove this mathematically, that if you start with mu1 and mu2 as shown here, then your red line will sort of divide some points or assign some of the points in cluster 2 to cluster 1, right? And why does this happen? Right, this is happening because given the mu1 and mu2s, right, given those centroids, you essentially sort of divide your space into two halves, right, in case of two clusters, such that each, right, so you're just taking the distance from each of mu1 and mu2, right? So this line is sort of bisecting the respective the line joining the two centroids, right? And it essentially points to the fact that because here the clusters are not of the same size, right? K means is running into, or in other words, K means is implicitly making this assumption that clusters are of about the same size, right? And if they are not, then it is likely to fail, like in this case, right? And which is sort of dissatisfying, because this is something we would like to we would like to handle in a real world setting, right? The second sort of case where k-means fails is as follows, right? So let's say, and this is one set of points, right? And this is in one cluster, and there is another set of points which is uh, the second cluster, and in some sense your clusters are these concentric circles, right? So this is cluster 1 and this is cluster 2, right? And this also is a pathological case for k-means, because even in this case, let's see what happens. So what happens is that if the points are exactly on the circles, then your mu1 and mu2 coincide with each other, right? And that's a problem, because if mu1 and mu2 coincide, then every point can belong to either of the clusters, right? Because we assign a point to the cluster whose centroid is closest to that point, right? So this is a problem. And in general, what will happen is that given this set of points, if I start with, let's say, some mu1 and mu2, which is maybe here, right? Let's say mu1 is here, and mu2 is here, right? So let's say these are my starting sort of centroids, then k means uh, eventually will converge to something like that, right? Let me draw it again, right? So it will converge to sort of a division of this space into two halves, where this is cluster 1 and this is cluster 2, and this probably will be your mu1, and right, and this will be sort of your mu2, right, starting from these green and the purple dots, right? And clearly this is not the right clustering, right, that you would like to achieve, right? So ideally your clustering would be something which, puts all, I'll not draw it here just to right, not to clutter the image too much, but your ideal clustering will put all your points um, in the inner circle in one cluster, and all your points in the outer circle in one cluster. And what has happened here, essentially, right, if you will, is that the clusters are not well separated, right? In this case, right, and when I say well separated, right, I guess it is more to do with sort of this linear separation, right, which essentially K means enforces, right? In fact, it will be interesting to think of a transformation of this sort of space, right? In fact, right, there is a quadratic transformation which takes these set of points into a different space through a quadratic transformation, where these points are linearly separable, and this is, very similar to the idea of what we have done in support vector machines. But given this particular set of features, right, in the current space, these clusters are not linearly separable, and that's why sort of k-means runs into trouble, right? And right, these two failure cases are something which really motivate us to design or think about other algorithms which can actually handle these, and that brings us to Gaussian mixture models. Okay, so let's get started with GMM, or Gaussian mixture models, right, which we will see can solve some of the problems that we saw with k-means clustering, right? And here is sort of the intuition, right? So once again, consider the set of points which we had seen earlier in the first failure case of k-means, where there are different size clusters. Okay, and what we will write, and these are sort of the cluster that we are looking at. There is a small cluster here, and then there is a big cluster here. The right side, this is cluster 1, and this is cluster 2, right? So right, so in Gaussian mixture models, the idea is that we will model the set of points using a mixture of Gaussians, where the distribution of points within each cluster will be described by a Gaussian distribution. In other words, right, so when we have, let's say, two clusters, right, each cluster is described by some mean mu1 and corresponding covariance matrix sigma 1, and similarly cluster 2 is described by a set of parameters mu2 and sigma 2, where mu2 is the mean of this cluster and sigma 2 is the covariance of this cluster, right? And this hopefully reminds you of something that we have studied earlier, which is GDA, or Gaussian discriminant analysis, right, where also we had this idea of points being distributed based on these normal distributions, but the difference is, in case of GTA, we had xi, yi, I equal to 1 to m, but in this case these yi's are right, and as we will see, these yi's will be replaced by these yi's will be replaced by these zi's, right, which will essentially denote the cluster assignment. Okay. With this intuition, right, let us try to describe the model, right? As in the case of GDA, this model will have two components. The first one will be sort of the prior probability of each point belonging to a certain cluster, which is essentially Zi, right? And Zi, this will be given by this multinomial distribution with parameters phi. And recall that this was, I think, an exam question in manner one, where we had more than one classes, right? So this phi in the general case is a vector of phi 1 to phi k, where phi l sum over l equal to 1 to m is right. And again, please refer back to the notes, uh, right, and also the minor question if you are not sure. So this is part one, right? And given these zi's, right, so once we sort of sampled, right, these zi's in case of GDA, right, once we know what is the cluster assignment for each point, right, which is zi, right, then we would be able to figure out the probability of generating each point, right? So xi given zi equal to l was given by this normal distribution, where this normal distribution had the parameters mu l and sigma l, right? And this is for all um, right. Right. So what are we saying here, right? So we are saying that we have a model which is very similar to GDA, but with the difference that we don't know the class labels, right? In this case, the cluster assignments. But what we could do is that right, if we could figure out the cluster assignments, then we know how to really sort of compute. Uh, the parameters of the model, right, which will be essentially theta given by phi mu l and sigma l, right, l equal to 1 to k, right. This will be our parameters of the model, right. So if somehow we knew zi's, right, we would know uh, how to compute these parameters, and these parameters will tell us how the points are distributed within each cluster, right. But this is based on this assumption that we know zi's, but we don't know zi's, right. Therefore what we'll have to do is figure out zi's, right, somehow, and that we will do using inference or prediction, which will be compute probability of zi for each sort of point, uh, knowing what the point is and parameterized by theta, right? And these two steps will essentially correspond to sort of the E step and the M step, right? So this will be our M step, which is essentially uh, estimation of the parameters of this model, and this will be our E step, which will be estimating these probabilities. Right, so let me sort of reiterate so the intuition that right, we have these set of points in some dimensional space, in case 2D space, and we really want to figure out this clustering. And the way we want to figure out this clustering is via two-step process, where we model each point as coming from a mixture of Gaussians, where the probability of generating that point given the the class or the cluster assignment is comes from this normal distribution, right. And uh, right, in addition, right, we have these sort of prior probabilities, which is zi, right, which comes from this multinomial distribution, which is essentially representing the prior probability of each of the points belonging to a certain cluster, right. And this is a sort of a two-step problem, because one, right, that of course we don't know what zi's are, right? We don't know the cluster assignments, unlike in the case of GDA. But the second problem is that we don't know the parameters of the model, right, which essentially generate these points, which is this capital theta, which is this phi's, mu l's, and sigma l's, l equal to 1 to k, right? So this is a sort of two-step problem, and we will see that this is the E step that will be estimating these zi's given the theta parameters, and this will be our M step, which will be estimating these theta parameters given the zi. And we will see, just like in the case of k-means, they will go sort of back and forth, that given the zi's, we will estimate the thetas, and given the thetas, we will estimate the zi's. Okay, so now let's proceed sort of with the first step, and we'll sort of bring the pieces together, right? Or let's proceed rather with the second step, which is the M step, right? And this is in particular, we are doing this first because we have seen this in the case of GTA, that assuming that zi's are known, right? We want to estimate the theta parameter, right? Estimate the theta parameters, and because the dies are known, we know how to do this, right? Using exactly the GDA formula, which is remember that this theta is phi, mu l, and sigma l, right? And I will encourage you to refer back to the notes for GDA. The phi parameters or phi l parameters is simply the probabilities of each of the um, clusters in this case, which is essentially the proportion of points belonging to that cluster. So this will be indicator of zi equal to L sum over I equal to 1 to M divided by a total number of points. Okay, uh, and then the second one, uh, right? So these are phi L's, and once again, to remind you, we are computing these phi L's given the Zi, um, right? So this is essentially the M step, right? And then we can compute the mu L's, right, which is sort of the cluster means, is simply the mean of the points belonging. Let me draw a line here, right? So these mu L's are nothing but the mean of the points belonging to each of the clusters. So this will be indicator of Zi equal to L, and then take all the points which belong to this cluster I equal to 1 to M, and then divided by essentially number of points which belong to this cluster, right? I equal to 1 to M, right? So this is our mu L, right? And this is being done for each of the clusters. And finally, right, let me write it here, right? The sigma L, or the covariance estimates for the covariance matrix, is simply we look at the points belonging to that particular cluster, and for those points we compute the empirical covariance matrix, which is xi minus mu L, xi minus mu L transpose sum over I equal to 1 to M divided by number of points which belong to that particular cluster, right? And I have done this for the case when we have different covariance matrices for each of the clusters, but right, we could also generalize it, or we could extend it to the case when we have a single covariance matrix, tied set of parameters for various clusters, right? And let me sort of draw the diagram again, right, to keep the intuition alive, uh, right? uh, that we had these set of points here, right, which supposedly belonged to cluster 1, and these are points which supposedly belong to cluster 2, right? So this is cluster 1 and this is cluster 2, and given and these clusterings are given by these zi's, right? And given these zi's, right, what we are saying is that we can estimate the parameters for each of these clusters, right? So given the cluster assignments, right, we can in fact calculate the entire set of parameters of the model, which is phi L's, right, which is sort of the prior probabilities of each of the clusters, and not only that, also the mu L and the sigma L equal to 1 to k, uh, right? So given the cluster assignments, we can compute the parameters, right? It is important to note that that this notion of given the cluster assignment is very critical, because in reality these zi's are unknown, right? So it is only conditioned on some zi's, which may not be sort of the optimal, that we are able to get these parameters, right? And which is very similar to the case of k-means, where given the cluster assignments, we were able to compute the centroids, right? But because exactly because of the fact that these zi's are unknown, right, and we had some assignment which may not be sort of the optimal, right, we have to essentially now go back, right, to the next step, that once we know the parameters, which is sort of the prior probabilities of for each of these clusters, the phi's, and also the parameters of the corresponding Gaussian distributions, right, we want to now estimate our new zi's, if you will, right, given the current model parameters, right? And these new zi's hopefully will be an improvement over the previous cluster assignment, um, right? And this is sort of the iterative process that we would follow, and hopefully in the process, right, we would at every step we would improve the not only the parameters but also the cluster assignment, and we'll repeat this process until conversion, right? And you can see the sort of the similarity with the k-means idea, right? So this is sort of the E and M step going in sort of tandem with each other. Okay, so let us proceed with this sort of E and M step formulation, right? Let us look at the E step in more detail, which is essentially saying that given the theta parameters, which is phi, mu L, sigma L, right, L equal to 1 to k, right, figure out what zi's are, right? And right, this is sort of described again by this diagram, that given uh, right these parameters of the model, right, let's say, right, these are this is cluster 1, and let's say the corresponding parameters are given by mu1 and sigma 1, and the corresponding parameters are given by mu2 and sigma 2. And given these set of parameters, right, and also sort of the class probabilities phi's, right, we would like to figure out zi's. In particular, what it is saying is that suppose there is a point here, which is let's say xi, right, we would like to figure out the 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 zi assignment for this, right? And this essentially is equivalent to prediction problem, right? And I want to stress again that in this E step, right, once we have the cluster parameters, right, we treat each sort of Zi, the cluster assignment of each point, as unknown, just like in the case of k-means, right? Given the centroids, we would want to now reassign the points, right? So exactly in a similar manner, right, given these parameters of the phi parameters, and also the individual uh, mu's and sigmas of each of the clusters for each of the xi's, we want to figure out what is the right zi, Here is thing here is where things become interesting, because as we will see that the zi will actually be now a soft assignment, because given the parameters, what we can compute is probability of zi equal to L, zi belonging to a certain cluster, given xi parameterized by theta, right? So given the theta parameters, we can compute this probability, and this will exactly correspond to sort of the soft assignment of this point xi to different clusters. But let's just compute this first using Bayes rule. We will get P of xi uh, given zi equal to L parameterized by theta into P of zi equal to L parameterized by phi over P of xi parameterized by theta, right? And this is using Bayes rule. Rule. Uh, okay, and just to remind you, right? This is again, uh, you know, sort of the prediction problem, right? Or this is similar to the prediction problem for GDA, right? And these distributions are this is just a reminder that P of xi given zi equal to L parameterized by theta is nothing but described by this normal distribution, which is 2 pi raised to the n by 2 sigma L, and determinant of that raised to the half e to x minus xi minus mu L sigma transpose sigma L inverse xi minus mu L divided by 2 and negative of that, right? And this is essentially the expression for um, the normal distribution. Okay, and also uh, the P of zi equal to L parameterized by phi is nothing but phi L, right? So this is also known, right? And finally, to compute this quantity is P of xi parameterized by theta, we can use the law of total probability, which is P of xi given zi, correct, zi parameterized by theta into P of zi parameterized by theta, and then sum over all possible values of zi, right? So this is nothing but the normalization constant. And in some sense, right, we have seen this before, right? And if you are not sure, right, please go back and figure out and convince yourself that you can compute sort of the value of this entire expression, right? um, Therefore, right, in a sense, we can perform this e step, which is computing the probabilities of these zi's. So this is great, but there is one important sort of caveat here, which is as follows, right? That in this E step, right, we sort of computed or tried to find out these cluster assignments, and these were essentially computed in terms of uh, these P of zi's given xi's parameterized by theta, but these are essentially probabilistic, right? In other words, what we are saying is that we had these two clusters with parameters mu1 and sigma1 and mu2 and sigma 2, and for a given point, right, you know let's say xi here, right, we could compute these cluster assignments, but these are not 0 or 1, right? These cluster assignments are soft assignments, right? uh, right? So each point, right, in this each step, after this each step could belong to multiple clusters, or would rather belong to in general would belong to multiple such clusters. And that poses a challenge for the parameter estimation in the next step. Remember that the entire sort of algorithm was to repeat this process, iterative process, that once we know the parameters, compute zi's, and then given the zi's we wanted to compute the parameters. But how do we compute the parameters if we don't really know sort of the hard assignment of zi's, right? If we don't know exactly, right, to what cluster a point belongs to deterministically, then our previous equations don't really work for the m step, right? But the solution is very simple, that in fact we can generalize, right, our m step computation to work with these soft assignments. Right, and right, in fact the hard case will come out to be will fall out as a special case of this soft right, parameter computation using soft assignments, and um, right, and right, let me write the expression. So the phi l would simply be, remember, we had indicator over points which belong to cluster L, but instead of that indicator, now we have probability of Zi um, given Xi, um, probability of Zi equal to L given Xi, um, right? Uh, Parameterized um, by the set of parameters theta t. Now let me sort of put this t, and this is t plus 1, right? And this is denoting that I'm computing my parameters at time step t plus 1 using my estimation of cluster assignments at time step t, right? So therefore I use theta t to compute these probabilities of zi equal to L, which are sort of the soft assignments, and the rest remains the same, right? So just right, instead of this indicator that we had, right, we have these probabilities, and then sum over all possible examples, right, divided by the total number of examples. Right, so once again, this generalizes the previous sort of hard assignment, because now we are saying for each point, right, compute your estimated probability of that particular point belonging to cluster L, and then sum of these probabilities across all the points, and that gives you sort of the prior probability for cluster L, right? And similarly, right, we can compute uh, x sorry, mu L, right, which will again be sort of using the soft assignment. So instead of indicator, now we will have mu sorry, p of zi equal to L given xi, right, and this is using the sort of the parameters at iteration p, right? And then with this probability, right, that this point I belongs to cluster L, we will weigh this example xi, each of these example xi I equal to 1 to m, and then divide by total number of points which belong to this cluster, where the number of points is again computed using this soft assignment, right? And this is essentially your parameters at time t plus. And I will not derive this here, but I will just say similarly, right? Generalize or compute sigma L e plus 1 in terms of soft assignment. Uh, in fact, it doesn't hurt me to write just in one single expression. To let me just write it for completeness sake, that the sigma L's will be nothing, using the soft assignments will be nothing but P of Zi equal to L given Xi parameterized by theta at time t, and then Xi minus mu L's uh, and Xi minus mu L transpose, right, sum over I equal to 1 to m, right, and then divided by sum over I equal to 1 to m of P of Zi equal to L given Xi parameterized by the parameters at previous time step, and this is at time t plus 1, and you do this for all L, right? So this is sort of the complete set of parameters, right? And this essentially gives us the entire right sort of the GMM algorithm, right? The Gaussian mixture model algorithm for computing these clusters, and also these densities or probabilities, which uh, is as follows, right? So you start with this set of points, and right, you initialize your theta 0, which is right initial set of parameters using some random initialization. This is your step equal to 0, and then you repeat this, do this the E step and the A step, right? So the first one is given theta t, the current set of parameters, right? Estimate the cluster assignments, which is P of Zi given Xi parameterized by current set of parameters, and this is exactly the E step or the A step as we have been talking about, right? And then the next step is given uh, the cluster assignments, which is these soft assignment P of Zi given Xi parameters by theta, uh, estimate the new set of parameters, which is theta t plus 1, right? And then of course t goes to t plus 1, right? So the iteration changes, and this corresponds to the B or the M step, which is the maximization step, right? In fact, right, right, let me just complete this. You do this until convergence, right? And how do you detect convergence? Uh, is right. How do you detect convergence? Is think about it, right? This will be when there is right very little change, right? No change, or essentially delta change in the set of parameters, which will also mean that there will be very little change in the set of cluster assignment. Right, note that here, because we have soft assignments, so we'll have to use some kind of threshold to converge or to stop sort of iterating this process. One more remark, I think, which I want to make before we break for the next class, is that now this E and M step would make sense, because right, these names, because E step is sort of computing your expectation, right, or expected value of these right, or probability of these Zi variables, uh, right, given the Xi and the current set of parameters, right, and the M step is computing your estimate or maximizing your thetas, uh, right, maximizing with respect to thetas given your current cluster assignments, right? And as you will see finally, right, in the next sort of class, that this entire process converges to a local optima of a suitably defined function, right? So this entire sort of E and M step process converges to the local optima of a quantity, which will be expressed in terms of likelihood, and this will lead us to the EM, or sort of the expectation maximization algorithm, which will sort of generalize this GMM idea to a broad class of problems, and we will study that in the next class. Thanks.